Well, hello there. This is Mrs. Sharp, and the first thing I would like for you guys to do is to check your book problems and your practice problems. So if you would go ahead and switch papers with someone and make sure you have a marker in your hand, just a marker, no pens, pencils, and we are going to actually keep track of some points here and make sure that when you are correcting somebody's paper today that you make the necessary changes so that they are looking at something that is complete and correct. So here we go. We're going to start with book problems number 34. Compare and contrast chemical reactions and nuclear reactions in terms of energy changes and the particles involved. So in terms of compare, chemical reactions and nuclear reactions are alike in the terms that they both have energy changes. And so we're looking for nuclear having more of an energy change, however, than chemical. So give them a point for that. Nuclear reactions deal with the nucleus, however, and chemical reactions deal with the rest of the atom. So give them a point for that. So all together for number 34, we're looking for 2 altogether. So they both have energy changes. Nuclear is way more than chemical. Nuclear is in the nucleus. Chemical is in the electron cloud. 2 points. Number 35, it says match each numbered choice on the right with the correct radiation type on the left. So A is alpha, so that's worth a point. B is beta, and C is gamma. So number 35 is worth 3 points each, or 3 points total, sorry. 1 point for A, B, and C each. Sorry, I think I misspoke there. So A is number 2. Alpha is 2. That's a point. Beta is 1. And gamma is 3. Not first, second, third. Plus 3. Alpha 2, beta 1, gamma 3. Here we go. Next. Number 36. Here's your figure showing alpha particles, beta and gamma, passing through the screen in between 2 charged plates. What can you infer? Here we go. A is beta because it's negative, so it must be attracted to the positive plate. So that's worth 1. B is gamma, so it goes straight through, no charge, no effect. C is alpha, so it is positive, attracted to negative, and repelled by the positive. So 36, also worth 3 points. Next, uranium-235 is used to make dental crowns appear brighter. The alpha decay of uranium-234 produces what isotope? Well, if I take uranium, and uranium is 92, and its mass number is 234, and I take it through the process of alpha decay, which you guys are going to do a bunch of these today, I would get an alpha particle, and the remaining isotope would have a mass number that went down 4, so 230, and an atomic number that goes down 2, so 90, and that would leave me with thorium. So 1 point for saying it's thorium, 1 point for having the mass number be 230. If you wanted to just write this instead, you could. So that's the isotope that is created. Sometimes that's called the daughter isotope. And that is your alpha particle. So 2 points there. Next. How does gamma ray emission affect the atomic number and mass number of iridium-192? It has no effect on either one because it has no mass. It does not matter. Gamma does not affect the composition of the nucleus. So 1 point for that, please. Number 40. One method of producing thorium-230, which we just saw, is through the radioactive decay of actinium-230. Is this alpha or beta decay, and how do you know? Okay, it must be beta, so 1 point for saying it's beta, and then 1 point for your because. The mass number stays the same, so it can't be alpha. Alpha would go down by 4, and the atomic number goes up 1, which is like beta, whereas it would go down by 2 with alpha. So 2 points there. Next, number 41. During the process of promethium-147 emitting beta particles, promethium changes into what element? Okay, so promethium, whatever this is, its atomic number is going to go up by 1, and its mass number is going to stay the same. So 1 point for having your mass number stay the same, which would give you 147, and 1 point for saying it's samarium, which is an atomic number 1 greater than promethium. So 2 for that guy. Okay, next, calculate the neutron to proton ratio for each atom. So you're going to get 1 point for each one of these. Tin 134 has a ratio of 1.68 to 1. Silver 107, 1.28 to 1. Carbon 12 is 1 to 1. And carbon 14 is 1.3 repeating to 1. That's just taking your neutrons and dividing by your protons. So for example, in letter D there, we have 8 neutrons and 6 protons. And if you divide 8 by 6, you get 1.33. So for every 1 proton, there's 1.33 neutrons. Remember, that ratio is what indicates the strength of the strong force, so it's important for us to know that ratio. Carbon 14 is radioactive, whereas carbon 12 is not. So carbon 12 has a very stable, good ratio of 1 to 1. Carbon 14's ratio is not so good. It's too high, 1.33 to 1, which makes it unstable and therefore radioactive. So that was worth 4. Sorry, that last one was worth 4. 51. Complete the following equations. Whatever you're missing there is going to be worth 1 point. So in letter A, you are missing your isotope left over. That's lead-210. So 1 point, please, for the mass number going down 4. 1 point for knowing it's lead, or for your atomic number going down 2. Letter B, what's happening there is beta. I know that because 239, your mass number is staying the same, but your atomic number is kicking up by 1. So saying beta is fine, or saying E 0, -1 is fine. So 3 for 51. Next, 52, alpha decay of americium-241. If it's alpha decay, you should be having an alpha particle, so make sure you have that, and you should be probably writing it this way. And then 1 point for knowing that your atomic number goes down 2, resulting in neptunium. 1 point for your mass number going down 4, which makes it 237. Plus 3 altogether. Number 53, same idea, just beta this time. So again, 1 point for your mass number staying the same, and for your atomic number going up by 1. 1 point for your beta particle, so a total of 3. And that's it for book questions. So add those points up, and if you would put that at the top of the piece of notebook paper that those book questions are on, that would be delightful. Thank you so much.